am Shashank, founder and CEO of KOOKI, where Sudeep, Sugam, all of us work together as he explained. So before dealing with the data sheet and user manual, etc., we'll go with the ARM architecture first. Okay, I am sure you have studied about ARM in your regular curriculum, right? Before ARM, did you study about the different types of architectures that were there? Von Neumann, Harvard, RISC, CISC. Can you? Okay, you have not studied about 8051, but you have. You had that subject? Okay, great. Which architecture does 8051 use? Von Neumann, CISC. CISC or RISC? First tell me that. Okay. Is it Von Neumann or Harvard? Depends on? No. 8051 core I am talking about. Let's forget about which company manufactures it. That's not required. Okay. Difference between Harvard and a Von Neumann architecture. What can you tell me in one line? Any one of you, please. I am not able to listen. Yeah, you can. Yeah. So what does that mean is, in the Von Neumann architecture, there is one part of memory which will have data as well as the instructions. Both are there together. Now, in the Harvard architecture, both of those memories are separated. There is data in one memory, there is instructions in the other part of memory. Which one is more useful, do you think? Why? Because it is? Because it is faster to access different kinds of memory. There's one more thing. One of the drawbacks with the Von Neumann architecture is you can write a code which will write itself. Are you understanding? Because the data memory as well as the instruction memory are the same. So you can basically write a code which will write new instructions. Did you understand? You know the assembly instructions: load, store, moving, etc. So theoretically you can write an instruction which will go into the memory and it will be executed at some other instruction, right? You don't have to load the program from the PC, from the compiler. There you can write an instruction which will execute as a different instruction. So basically the code writes itself. That creates a huge security flaw which can hack. Sorry? Macros or no? Macros are something different. What it can do is basically someone can hack and they can actually write the code which replaces itself. That way the whole code breaks. Okay, that is Von Neumann and Harvard. Now what about RISC and CISC? You know the acronyms, you know the full form, right? Reduced instruction set and complex instruction set. Which was started first? So why did they move to RISC? Execution time is? Okay. In CISC architecture, for example, if you want to, in CISC instruction sets, for example, there is a simple opcode for addition of two numbers. Okay. Now there is an instruction for addition of two numbers. There is another instruction for addition of two numbers and storing it in a memory. There is one more instruction which retrieves a number, retrieves data from a memory, executes and stores it in a different memory. So there are different types of add instructions, right? So there are like 5 or 6 types of add instructions which can be executed. That is complex instruction set. Now in reduced instruction set, everything is replaced by just one instruction, add. Now what that add does? It will always add two numbers from a register. It will not access the memory, it will access the register and it will always add two numbers there. So in a reduced instruction set, the work of a programmer increases, the work of the software increases instead of a hardware. In the software, you will have to write different steps for addition and the moving of the data from one part to another. Whereas in CISC, you could have done it in a simple single instruction. But it creates a problem in case of operating systems. Now, when operating systems are designed for a CISC architecture, the compiler optimizes the code, right? Correct? Now, when compiler optimizes the code, it tries to get the results in as less steps as possible. Now, it was found that when a Unix operating system was compiled for a CISC architecture, it used only 30% of the hardware on the microcontroller, which was actually decoding instructions. All the other part of the microcontroller which was not used were actually being used for decoding instructions. There is a particular hardware for decoding instructions, right? So, only 30% of that hardware was being used in an OS. Now, that is why they decided to build a RISC based system, where the instruction sets are reduced, the work of the software increases, but it becomes faster, more the code density becomes huge, and the hardware can be effectively used, optimally used. What is the full form of ARM? Advanced RISC Machines. ARM actually doesn't have a full form now. It is just ARM. There is no full form for ARM. It started as Acorn RISC Machines. That was way back in 1978. So, in 1978, this company based in Cambridge, UK, so they built the Acorn RISC Machines. So, they were building the computers which were based on a RISC architecture. They had started it there, and they were building PCs mostly for school purposes, which were being used in schools. Now, after this Acorn RISC machine started, everyone came to know about the importance of RISC architecture and how it is effective in building a system. In 1990, Apple, VLSI Technologies, that's another company, and Acorn RISC Machines, all these three came together and they formed a new company called Advanced RISC Machines, Advanced RISC Machines Limited. That was in 1990. Because Apple wanted to use the RISC technology, the RISC computer set technology, but at the same time they did not want to partner with Acorn because they were considered a competitor for Apple. They were also into the business of building computers, right? So, that is why they built a partnership. Apple invested in the company, VLSI Technologies gave all the tools whatever is required for building a RISC microcontroller, and Acorn Computers, the one who built that, they provided 12 engineers. So, it started out with 12 engineers who built the first ARM PC, first ARM processor, that was ARM 1 way back in 1990. So, this is how the journey of ARM started. Now, by 1994, Nokia was the main player in mobile phones. So, they had a GSM phone coming up, and Nokia wanted a newer design. So, the guys at Texas Instruments, TI, they suggested Nokia to go for a ARM processor. But the thing was, all the processors back then used in the mobile phones were 16-bit processors, whereas this ARM processor designed by the ARM Limited was a 32-bit processor, right. So, that is why ARM custom designed a 16-bit instruction set specifically for Nokia, and they gave that name, what is it called? Thumb. That is what became Thumb instruction set. So, the first GSM phone using an ARM processor was designed and launched in 1994. That was Nokia 6110. Became a huge success, and from there on everyone followed the suit of using the ARM based systems. So, right now it is basically in each and every smartphone. Each and every smartphone uses an ARM architecture. 98%, according to the recent estimate, 98% of the whole smartphone industry, every smartphone has a ARM processor in it. In 2007, 10 billion ARM processors were shipped. 10 billionth. 10 billion. Okay, that is 10 into 10 raised to 9. So that many ARM processors were shipped. By 2014, that number had grown to 1000 billion. So that is the reach of ARM right now. By the way, who owns ARM right now? Any idea? You guys don't read the news. So ARM is currently owned by the Japanese telecommunication company SoftBank. You have heard about SoftBank? No? It's a huge investment firm. It has investment. It recently invested in Flipkart, right? No, I guess that was the news of the world, right? Okay, let me. So right now, ARM is owned by SoftBank. It was bought by a record $31 billion. $31 billion were spent by SoftBank to acquire ARM. But the best thing about ARM is, even though ARM processors, you know, as like I said, billions of ARM processors are shipped every year. But do you know how many employees are there in ARM? Right now, it is hardly 3,000. In 2007, it was 400. 400 employees. Right? There are more students in this college than that. So with only so many employees, ARM is able to gain that much success. So you should read about this ARM, the history of ARM. It's quite interesting. So now let's move on to the technical part. Okay. Any questions till this time? Nothing? Okay, let's move on to the technical part. So this is a Cortex series microcontroller by ARM, right? Cortex series by ARM was started back in 2005 because they didn't, you have also studied about the ARM 7 TDMI, right? That is one of the most successful ARM cores till now, the ARM 7 TDMI. Now this Cortex was started by ARM in a way to expand their business. Initially ARM was only into the microprocessors, there were no microcontrollers. Then in 2005 they started with 3 series, Cortex A, Cortex R and Cortex M. Now Cortex A is an application specific processor. Most of your smartphones uses Cortex A. They use, I think the latest one is Cortex A57, something like that, that series. So that's an application specific processor, very powerful, can drive displays, touch screens, etc., etc. Too powerful, but at the same time expensive also, difficult to design. Then there is Cortex R. Cortex R is a real-time microcontroller. Real-time meaning the latency from input to output is very, very low. That is what real-time means. The Cortex M series, which is one of the largest selling series of R, is Cortex M series, which is the microcontroller series, which is the core specifically what they have built for microcontrollers. So those are used in basically most of the embedded systems. So like Sudeep said, in one of our products we have used the Cortex M3 process controller from TI. Cortex M3 processor, that's a GPS tracking system with all OBD analysis, car analysis, etc., etc. So all those things can be done on a Cortex M3 system, whatever you are now going to do on this. So now this controller is LPC1343. It is Cortex M3. Now it has 32 KB of flash, onboard flash, and 8 KB of SRAM. Right? You have worked on 8051. What was the flash memory and what was the RAM in that? Which one did you use? Atmega? ATS something? Which was the controller you used? The number? 89C51. Okay. What was the RAM and flash of that? flash was 4 KB and RAM was 256. Okay, so this processor has a 32 KB of flash memory and 8 KB of RAM. It has all the other peripherals, whatever is required to build a basic embedded system. It has serial interfaces, timers, GPIOs, everything. So with this present workshop, we'll be dealing with the mainly two parts. As he explained, in the application what we require is timers and GPIOs. Okay.